we propose PixHt-Lab, a light effect generation framework for image compositing. We assume the input is the image cutout and the background image. The outputs are the rendered light effect layers, including the reflection layer, the refraction layer and the soft shadow layer. Those layers can be used for the final image compositing to make the image compositing more realistic. One direction in the related area uses GAN-based method. The GAN-based method takes the object mask and background images as the generator's inputs, and predicts the compositing results based on the background image lighting conditions. The limitations are the following. First, the background image is always assumed to be given. But for indoor studio setting, the background is empty most of the time. The second limitation is that there is no controllability over the shadow direction. Also, GAN-based method cannot render soft shadows. Previous work SSN addresses the controllability problem. However, it assumes the shadow receiver is a ground plane and objects are standing on the ground. A follow-up work SSG addresses the limitations by SSN. SSG can render shadows for general surface. And they propose a method to render specular reflection based on their proposed pixel height representation. SSG also has some limitations. One is that general surface soft shadow rendering is challenging and SSG fails to render realistic soft shadows. Another limitation is that the reflection rendered by SSG is limited to the specular case. Our work instead renders controllable physics-based reflections and more realistic soft shadows on general shadow receivers based on the pixel height representation. The pixel implicitly encodes the relationships of the camera intrinsics, extrinsics and the 3D space. We present the mathematical relationship between the pixel height space and the 3D space. Given a camera center O', with its 3D height h, and the camera intrinsic vectors a, b and c, each point P' on the image plane and its corresponding 3D point P has a projective relationship. By the pixel height representation definition, the Q is the foot point of P, so the Y of Q is 0. Solving the equation, we can get the W for the P, then we can recover the 3D point P. In other words, the equation connects each point in the pixel height space to its corresponding point in 3D. Given the input cutout, we first predict the pixel height for the foreground cutout and background. Then 2.5D information like the normal and depth can be reconstructed by our presented equation. Based on the 2.5D information, our proposed renderer can render lighting effects, like the reflection and refractions. To render realistic soft shadows on general shadow receivers, we propose 3D-aware buffer channels for neural soft shadow renderer. SSG uses the pixel height and the hard shadow mask to guide the neural soft shadow renderer. We propose to utilize sparse hard shadows and 2.5D distance defined in pixel height space as the 3D-aware buffer channels to help the neural renderer better understand the 3D relationship between the shadow occluder and shadow receiver. Experiments show our proposed 3D-aware buffer channels render better soft shadows comparing with the previous state of the art. Here are more results. Based on our pixel height and 3D mapping formula, we can provide low-level detailed reflection control by the change of surface materials, like the glossiness and Fresnel coefficients. Here is one more real-world example. Our PixHt-Lab can cast realistic soft shadows on the wall and the realistic reflection on the ground. Thank you for your attention. To conclude, our core contributions are first, a mapping formulation between the pixel height space and the 3D space. Second, we propose a 3D-aware soft shadow neural renderer for shadow rendering on general surface.